Okay? So, and this is a little bit of background information that we may or may not even care about, but I'm going to tell you anyway. So, as a science department, we are kind of transitioning what we teach in what grades. Okay? So for a really, really long time, in 8th grade science, we didn't do any waves or any pendulums or any of that at all. Okay? So we used to teach this at the very beginning of 9th grade. Then we started changing what was going on in 8th grade, so I kind of transitioned to what we were doing in 9th grade. And this year's kind of a funny year in that we're just kind of like bouncing around things. I know that you've talked a little bit about light, right? Last year, I think. And most of you took 8th grade here. Maybe some of you are like, oh, maybe not me, but that's okay. We'll get you hooked up. It'll be fine. So some of this will be reviewed, but I am going to go deeper, like really fast. Okay? And I want you to engage with me on that deeper level, not just like, oh, I get it, I'm fine. Okay? I want you to ask good questions. I want to have a good conversation with you today. Okay? When you're talking, we may do a lot. It just kind of depends on how things go. And then we'll kind of bounce through from there. Does that sound okay? Does that make sense? Okay? So the big topic for the day and for the unit is light. And I know you talked a little bit, I think, did you talk a little bit about light last year in 8th grade? No? So I want to do kind of like we did with energy, I don't know if you remember, a little bit of a brain dump, like what do you know about light? Does that sound okay? So that I'm not repeating everything that you already know, but so we can kind of start on an even playing field. Does that sound okay? So I'm going to give you, let's say, a minute. You don't have to tell me what kinds of light or what, like, but just write down facts that you know, things that you remember either from last year or that you learned in science or you learned somewhere else that are things that you remember about light. Does that sound okay? Okay. So I'm going to start the timer right, I don't know, now. Go ahead and write for 1 minute. Go. Come together. Let's have one conversation now, shall we? Yes, please. So we're just going to kind of go table by table. I feel like this usually works pretty well. I want to make sure, so there may be some things that we have conversations about now, or maybe some stuff where we make a list for a bit and then we have conversations on later. We're just going to kind of make it organic. Whatever happens, happens. Is that okay? Alright. Let's start with this table. They look excited and like they want to show something. That was one thing. There's one thing you said that you want to put out there as something that's true about light.
All colors make white light.
Okay, all colors. You guys saw that? I heard some color conversations happening. Cool. Alright, I'm just going to keep going. Is that okay? And then we're going to talk about this. We're going to get into it. It'll be a good conversation. Let's start here. Let's go to the next. So, you know, some sort of fights going on at this table. I don't know what's going on. Karen has to share something with us.
White, the color white is white is black.
Okay. Oh wait, white reflects. Let me try it again. Awesome. So if you don't have these written down, if you want to add these to your list, that would be a really cool deal. So what else do you say?
There's different kinds of light.
Different kinds of light. Do you want to explain them all out? And you don't have to. You can just leave it right there. Just leave it right there. Okay. Different kinds of light. I like it. Awesome. And we're going to expand all this stuff in just a little bit. I just want to get some ideas out there. Let's see. Which one do you guys say your back's over there?
So there was a wave and a particle.
A wave and a particle. Did you guys talk about that last year?
Schoenberg system.
Oh, Schoenberg. That's true. Yeah, there's so much cool physics going on there. John, what else do you guys say? And you can pass if you want to. That's okay.
I said light is faster than sound.
Light is faster than sound. How come you didn't discuss it? Just. Oh, they're okay now? Okay. It's quick turnaround, I'm impressed. Nice work, nice work. And then what else do you guys say back there?
Like most of our stuff right inside.
Oh, okay, that's totally fine. That's totally fine. Other people at your table? I mean, we have a lot of stuff listed already. Lambda. Lambda. It's a Greek letter. There it is. We can look up here on our list. You see the thing looks like a K? Thing looks like a K, yeah, the capital K up there. That's actually the Greek letter kappa. And the one right after it is lambda. And the little lambda, the one that the second one, is this one here. Yeah, and lambda does have something to do with it. We'll talk about what it has to do with that in just a little bit. Yeah. All right, over here. Jake, what else do you guys say? Or we did everything?
Some colors can be bright, some can be not as bright.
Okay. Alright, we've gone around once, is that right? So I'm just going to make it a free flow for just a moment. What are the things that you want to add to the list? Go. Light doesn't bend. Okay. Ever? Okay. Abdul, what you got? Light is energy. Yeah.
Those particles are called photons.
Particles called photons. Cool. Go.
Can be reflected or refracted.
Oh, lots of good words coming out here. There's something doing it. I'm going to go land on hook. C. Yeah. Is that okay? Yeah. Yeah. Has frequency. Awesome. What else you got? So that kind of tapping everything. Yeah.
Its speed is frequency, motion speed.
It is. It's fast, right? 3.0 times 10 to the 8. What? Oh my god, I'm serious. Oh, that's simple. 3.0 times 10 to the 8. 5 is 4. Oh, like, I don't know. Other things you want to add to this before we kind of pull this apart and figure out what all this means? This is a really awesome list, you guys. I have them like, whoa! So there's some kind of chunks here I'm gonna make so we can make a little more sense of this. I put these things together because they kind of fit together. I'm actually gonna put this one with it. Woo! So those are a little box around, so we'll play with those. I'm gonna put this statement here about bending light with this statement here, because those kind of go together. I see some things, a bunch of things about colors. Let's talk about that together. And that kind of fits in with this different kinds of light thing, because that's huge too. Yeah. And we're going to start actually, I need to put a blue box around that one. That one goes with this one here. We're going to start right here. Does that sound okay? Okay. So we talked about, and we put a blue box so I don't forget. Just attached to that. Yeah. Alright. Not we, because I didn't teach you in 8th grade. I'm going to get you into now. You talked about waves in 8th grade, right? Yeah. We talked about waves, and I don't know how to do a whole brain dump about waves, but you know that a wave carries energy, right? Okay? And there are lots of different kinds of waves. Can you tell me some different kinds of waves real quick? Yeah. Transverse. Oh, have you guys heard that word before? Do you know what transverse waves are? Right? Where the medium is oscillating perpendicular to the direction of wave motion. Does that sound at all familiar? Yes or no? Yeah, a little bit like maybe I heard that a year ago or something. Sure. So if we talk about these waves, They can be transverse. Do you remember the opposite of transverse? You were almost there. Longitudinal. Yeah, you got it. We got it the same thing, so I got that. So a transverse wave is one, just, some nice little memory things here, where it's perpendicular, we should say, the motion. Did you guys talk about a medium? Does that sound like a word that you know? Motion of the medium, the thing the wave travels through, is perpendicular to the motion of the wave. So if I have a string, and I'm going to make a transverse wave, I move it like this, and the wave moves that way. That sounds familiar to you? Yeah? Longitudinal? What is that one? It's opposite. It's the parallel one, right? And I don't know if your teachers taught you this cute little way to remember this. The transverse starts with a T, right? And this looks like an upside down T. Did you guys talk about this? I don't know if you could answer. I'll tell you something new. There you go, boom. Okay, longitudinal, the motion of the medium is parallel to the motion of the wave. And the trick here is that longitudinal starts with a what letter? And it ends with an, and if you put those L's together, they look like parallel lines. Does that make sense? So that's like my little mnemonic, or I don't know if it's really mnemonic, but the way that I remember that, right, is that you got the L's, like this and like this, and then they look, just like that. What else do you know about waves? What kinds of waves are there besides those kind of distinctions? What can a wave be made by? Or what can it be? Yeah.
I know there's a wave where they add together magnitudes.
Yeah, does anyone know what that's called? Oh man, this is like. So there's a word called superposition. Did you hear that word once? Yeah, and I was like, I guess. Superposition means when you have two waves that go together, when they add together, you have a source with C. Anybody know? Constructive interference? Yeah? And when they go back and they cancel each other out, then it's what? Oh yeah, it's all coming back. Yeah. Constructive and destructive interference, absolutely. What can waves be caused by? What can they go through? What's that? What did you say? It's kind of a big question, so lots of good answers. What did you say?
Can they go through a wall?
They can go through a wall, right? Can a wave go through a wall? Yeah. Right, so he's got the little part of his womp. Yeah? Does that make sense? Yeah. Some of those waves, generally, when you're talking about waves that are going through walls, we're talking about things like sound waves. Sound waves are the vibration of particles, right? Because of something like, I don't know, my vocal cords, right? The little muscles in my throat are like, pushing the air that's right up here, pushing that air, and it's going towards your ear. Yes, is this making sense? Does this sound like you've done this before? Did you have this conversation maybe with somebody who's a little bit less weird than me? Right? And it's going towards your ear, and then it vibrates your eardrum, and that's how you hear? Yes? Okay? But a sound wave, you said something about sound waves earlier. Can you see what sound waves? Going faster, right? Than sound waves. Does anybody know how fast a sound wave goes? 30 stuff, right? It depends. It depends on what it's going through. It depends on how cold it's going through air, how cold the air is, how dense the air is, right? If you go up to Denver, right, where the air is a little bit thinner, then it's going to move at a different speed. But we're talking things on the order of, so V is for velocity, right? So the velocity of a sound wave is on the order of about 340 meters per second. And the other thing that's really important to know about a sound wave, what does a sound wave have to have in order for it to travel? It has to have a source. Everything has to have a source, right? But it also has to have a what? It has to have a medium, right? A sound wave must have a medium. And not like a large or a small, but a medium like what? What does that really mean? Oh, wait, yeah, so what is it? What is the medium? Has something to travel through, right? So I can travel through air, right? That's how I'm talking to you, okay? Again, my vocal cords, wah, 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 and then it's moving through the air to your eardrums, okay? If you go stand in my back room and I'm standing out there, you can probably still hear me, partially because there's air underneath the door, but also because it's traveling through the walls, right? So you can have it travel through things. What can a sound wave not travel through? A vacuum. Right? Have you guys heard of a vacuum? Does that word sound familiar to you? And again, not like the thing that you have to use on Saturday mornings and ready to go out and play, right? But like, what is a vacuum in science? What does that mean?
A space with no air.
Yeah. It's a space with nothing in it, right? There are no particles, there are no anything. So it must have a medium, so that means that sound cannot travel through a vacuum. Vacuum's such a cool word because it has two U's and I think that's a problem. I don't know, I like double U right from there. It's fun. Anyway, so what does that mean if it can't travel through a vacuum? That means that our world in terms of watching movies is often crushed, right? When you start watching sci-fi movies, and they're like the people that are out there in space. There were a couple of movies that came out in the last 2 years where people like get stuck out in the middle of nothing. Wasn't there one? Yeah, I didn't see it, but that's what I feel, right? And like the people like, ah! And like screaming for help. Two problems with this. So, a vacuum, outer space is a vacuum, right? Or pretty darn close to it, because there's no air out there. So number one, if you just open your mouth, right, then your lungs are going to collapse, so that's a problem. So you don't want that in number one. Number two, so let's say, what's that? Yeah, because there's a whole air pressure thing, and but there's no air, it's bad. So don't try that. So maybe, if you go to outer space, and you know that much, you can't tell, you know that's not a good choice. You need some sort of emergency way to let people know, so maybe you bring your tuning fork with you, yes? Maybe you bring your tuning forks, yeah. Yeah, so the tuning fork, right, so you put it in your pocket, everything's good, so I have enough things to do in the lab and so, tuning forks, right, you've studied these before, you actually do, right, and you strike a tuning fork, and it makes a noise that you can't hear right now, but you put it to your ear, oh! It's a nice sound, right? Okay, because how it's doing it? It's taking this wah, 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 just like your vocal cords, wah, 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 right to your ears. Does that make sense? So I'm going to take my tuning fork out into outer space because then I can send a signal, right? Help me! Hey! Right? Like, problem! Right? There's some kind of issue. Okay? Can I strike my tuning fork in outer space? I think that, why not? Right? Like, I can strike it, but is anybody going to hear it? Is the tuning fork going to vibrate? The tuning fork will vibrate back and forth, wah, 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 but what is there none of right here? There's no air! So there's no air to vibrate so nobody else will hear it, right? Even though it goes this, because there's no air between my ear and this. Not going to happen. Does that make sense? What's that? I know! It's crazy! It's crazy! So here's the thing. That's all sound. It's important to know that sound does not travel through your vacuum, so you can't hear it. You can't hear anything in space. So I'm a huge Star Trek fan, right? I really like Star Trek. I watch it a lot. And they show, like the Enterprise going through space and like, no, not happening, right? Does it make noise? No. Well, I guess it depends on how you look at it, right? Like when the engine's fired, is there the stuff that happens there, but does it travel anything beyond that? No, because there is no air there for it to travel through. I think there was a question that was given in somewhere. Yes. Oh no, did you just forget it?
Yeah.
Steve, if you think of everything else, fair? Okay, so sound is interesting, but there's a lot of limitation to it. Oh yeah.
Wait,
radio waves travel through space?
Right! Because radio waves are not sound waves. What? That's weird. You turn your radio on and you hear stuff, right?
Yeah.
Yeah!
I think that's how it
Right. Yeah. And that works. So, we got a couple things that are put together to make that happen, okay? Go. Oh, what do you want?
If you're not talking about something.
I'm not talking about anything, Zach. It's all you.
Okay. Like, isn't it like all the radio waves ever going out of space? So you could flying past what we could go and listen to 10 12.
Yeah. We'll get there. Yeah, it's true. All right. I know, it's a great day today, right? Okay. All right. So sound, we understand sound pretty well, yes? You talked about this last year, so you had some kind of trying to think about it and that sort of thing. You talked a little bit about light maybe last year too, but we're going to go further now. So here we go. So light. Has a speed that it moves at also. You mentioned in the list of things that we know that it moves a little bit faster, yes? Yeah. The velocity of a light wave, of any light wave in a vacuum, is the fastest that anything can move. Okay? According to all of physics, that's a lot of stuff. Our understanding is that nothing can move faster than the speed of light in a vacuum. The speed of light in a vacuum, we usually don't write V, we usually write C. It is a constant. The speed of light in a vacuum so I just want to write vacuum again. How fast does light go in a vacuum? It's true, but there's a number for it too. I wanted to know the number. I'll go to that in just a second. Yeah. Okay, and that's approximate, but it's pretty close, and it's close enough that we can use it. 3 times 10 to the 8 meters per second, that's like a big number. Let's just kind of think about what that means. 3 times 10 to the 8, so that's 3, 0, 0, 0, 0, 0, 0, 0, 0. How many zeros? One more? 2, 3, 4, 5, 6, 7, 8. Okay? So that's... We put some commas in here. There's a comma there. There's a comma there. So this is what number actually? 300. This is thousands. This is million. Of this. Okay? 300 million of this every second. That's really fast, okay? Nothing can go faster than that speed. In fact, this is a little bit of just kind of more information because this is just what I do. Nothing with mass can go that fast. It is not possible. It is what they call the cosmic speed limit. Okay? Nothing can go that fast if it has mass. So that would lead us to believe that light must have no mass, right? It can't if it goes fast, right? That's ridiculously fast. Okay? If light goes through something else, will it always move that fast? No. It can slow down. We can get light to slow down, okay? Then it goes, like 2.96 times 10 to the 8 meters. Like it goes a lot slower. Appreciably slow, and we can find out some cool stuff about that. But this is as fast as it can go. Okay? We can use that information to figure out things when we talk about things in astronomy all the time. Okay? So in upper level physics classes, we do astronomy. It's super fun. I hope you come play with me and do it sometime. But we're just going to kind of touch on it really quickly here. This is kind of going to what Zach was talking about and kind of going to other things as well. So, before I go there, though, I keep getting excited here. Does light need a medium to travel through? Is it a wave? Let me ask that first.
Yeah.
Light is a wave, right? Sure, I guess, yeah. Does it need a medium?
No.
What evidence do you have that it doesn't need a medium?
You can see the sun.
Yeah, you can see the sun. It's a good thing, right? If light couldn't travel through a vacuum, friends, we would not be here. Okay? In so many ways, we would not be here. Like, not even just you wouldn't show up to school, but like, we would not be living. There would not be light, right? Like, that wouldn't happen. So that's something we need to know, is that light can travel through a vacuum, of course. Okay, we mentioned this before, but I'll say it again, that it can also travel through a medium. But it slows down. And that's important. Okay. Our evidence, I was going to write that down. So we know that we can travel through a vacuum is that we can see the sun. And the sun is giving off light, right? So that's pretty nice. How far does that light have to travel? Does that have to travel a long way?
93.
She's making stuff up over there. I don't know. Is that the right answer? I don't know. I never can keep track. I do know this. On a what commercial?
On a commercial for those raisins things with the sun-made raisins.
Advertising works. You can know. That's awesome.
It was 93 million miles to grow your grapes.
That's awesome. I don't know how I missed that commercial, but it sounds great. Oh, okay. I like it. All right. This is fantastic. So, we can see the sun. I will tell you that the light from the sun, the light that we see right now, if you look out the window, oh, there's the sun, yay! The light that you see is not the light that just came from the sun right now. It's old, right? It's old light. It's 8 minutes old. Yeah. So the distance between the sun and the earth, generally when we talk about distances, we talk about things in terms of meters or kilometers, right? But we can also talk about it in terms of these things called light minutes or light years, yeah? Have you heard the term light year? Yeah. So a light year is a measure of distance, not a measure of time, even though it sounds like maybe should be, right? It says year, it should be time. No. Okay? Distance between the sun and the earth is 8 light minutes. Okay? What I want to know, we need to confirm or deny Maya's recollection from her childhood of watching sun-made raisin commercials. I would like you to tell me, let's figure it out in meters first, and then we'll do the conversion from meters in a minute. Okay? With your table mates, I want you to figure out how many meters 8 light minutes is. You can do it. It's going to take a little brain work. You'll probably need a calculator. Go. What do we get? What do you get for a number? Let's go, Skyler. 1.4. What do you guys think? Do you agree with it? Yeah. Somebody feeling okay with that? Either you know how to do it yourself or you got some brain power help with from your teammates? So then, Maya, what did you say you thought it was in miles?
93 million.
93 million. I'm not saying you're wrong. Approximately. So, what do you know? How can you relate miles and stuff? Because now I want to just convert it because I'm just curious. Wrong answer. I mean, yes, you can, but I want you to use your brain. Okay, so they're about 3 feet in 1 meter. It's not exact, but it's close. And how many feet are in a mile? Look at this girl. She's like, I got that one. 5,280 feet in 1 mile. So now, I want you to figure out how many miles it is, and we'll see if the summary people were lying or not. Go. So sometimes people get kind of freaked out when you're just converting things, friends. And instead of yelling at each other and fighting about it, let's just set it up. So we got 1.44 times 10 to the 11th. Then, if I want to convert that to feet, I'm going to do 3 feet is 1 meter. Does that make sense? Yeah? Because there are going to be more feet than there are meters, right? Does that make sense? So I'm going to multiply, so I'm going to cancel it out. And then I want to convert some feet to miles. So where am I going to put the feet now? On the bottom. So 5,280 feet in 1 mile. Is that okay? So we're going to do 1.44 times 11 times 3. Divide by 5,280. And what do we get? And the number?
81.
81 times 10 to the 7th? 8.18 times 10 to the 7th? Miles. So, if we write that, it's going to be 8100000. I can't count zeros here. So it's 1, 2, 3, 4, 5, 6, 7. So, yeah, I mean, this is on the right order of magnitude, right? It's about 100, and that's about, that's pretty close. And, I mean, it's not exactly 8 light minutes, it's close. I mean, so like, some approximations have it. I think that some nature much is okay. Good for them, and good memory for you. There you go, 93 million miles. I just remember 8 light minutes, that's what's 6 in my head, okay? The thing that I want you to know, not only just that you can do that and you can figure that out, is that if somebody had the power to turn the sun off, which is not the way that our solar system will end its life, but let's say it was, let's say that, I'm thinking Maggie, she looks like she may have some sort of superpower, be able to snap her fingers, and when she snaps her fingers, the sun turns off. I'm done, no more fusing. Okay, so it's done. Boom, are we going to know? No, we will know 8 minutes later, right? Because the light that we see right now is 8 minutes old. Okay? That's kind of weird. It gets even weirder when you start looking at the night sky. Okay? The stars that you look at are closer or further away than the sun? Further. The sun is the closest star, yes? Okay? Closest star is the sun. After that, they are pretty far away. Okay? On the orders of light years away, yes? So the light, are you guys okay over there? Do you need something? You okay? Okay, stay with us, please, thanks. Meaning that it takes the light years, hundreds of years to get here. Meaning that the stars that we see are likely, especially the ones that are really, really old, are dead, are gone. They don't actually exist. They're not there anymore. That is messed up and weird. Okay? So if you think about, you guys, you know a little bit about the structure of the universe, I'm guessing. So you know that the sun is at the center of our solar system. So you've got the sun, and then you've got, the planets, including us, right? But our solar system is just a pretty little piece of what? The Milky Way galaxy, have you heard of this? Yes? The Milky Way galaxy is very, very large. It looks kind of like the galaxy over there in that picture. That is not the Milky Way galaxy. If you ever see a picture that says the Milky Way galaxy, you know that they are lying. How do I know that they are lying if they show me a picture of the Milky Way galaxy and say, look, it's the Milky Way galaxy? How do you know? We're in it. Have we ever left the Milky Way galaxy? No, we can't get, we could. We could send a probe there, probes that are on their way out. They're not going to be out there for a long time, friends. Like, your great-great-great-great-great-great-great-grandkids may get to have some information from them, okay? But, we've never been outside of the galaxy, which means we can never take a picture of it, right? Okay? You can't do that. But we know, based on things that we can see, so if you go out and you look at the stars, like if you go somewhere not like in Des Moines, but you go out a little way so there's not a whole bunch of ambient light, especially in the summer when it's really dark, you can see a really, really nice band of light, where there's a bunch of stars, It looks kind of milky, hence the name, the Milky Way, and that is our galaxy. That is like the plane of our galaxy, so you can actually see that in all of the stars that live in the galaxy. Most of the stars that we see with the naked eye are stars from our galaxy. Right? But there are thousands and thousands of galaxies that exist as well. Okay? The nearest galaxy to us, the nearest galaxy to the Milky Way, is Andromeda. So, it's a galaxy that's very similar to ours. We're in a little spiral galaxy, and that's a spiral galaxy as well. Okay? And it's got two little galaxies that live outside of these two bright spots here, 1, 2. Okay? And those little galaxies are little, what they call elliptical galaxies. They don't spin quite like that, but they're just kind of like this. But the Andromeda galaxy is the one that's closest to us. It's kind of our sister galaxy. Does that make sense? It's like the thing, like I said, it's closest to us. It is 2.2 million light years from us. 2.2 million light years. That means the light, if you go out and look at the Andromeda galaxy through a telescope, which you can do easily, you go to any observatory, say I want to see the Andromeda galaxy, and say, okay, where is boom? Right, you see it looks something like that, probably not quite as pretty, but something like that. A little fuzzy ball, okay? The light that you're looking at, like you're actually literally like the light's coming in, it's hitting your eye, here it is, right? That light is the light, not the king that night. 2.2 million years ago. May or may not still be there. Who knows, right? There's lots of unknowns there. I want you right now, just because I want to make sure that this makes sense to you, I want to know how many meters that is. Go. So let's come back together. Okay, so tell me what like how do we do that? Okay, so let's talk it through. So whenever I'm like stuck in my I don't know what this means, I'm always going to start with what I know. So the thing that I know is that it's 2.2 million light years away, right? Okay, so it's going to be 2.2 times 10 to the how many? Any idea? 6? 7? 8? 12? I don't know, what is it? Let's write it out. So 2.2 million. Does that look right? Yeah? So 1, 2, 3, 4, 5, 6 light years. So that means 2.2 years that it takes the light to travel that distance. Does that make sense? Is that okay so far? Okay. What do you do with that information? How do I get that into meters per second? Like, what does that even mean? What does that mean? Okay. So like let's convert years. Okay. So the light thing just means the speed of light. So it's going to take this many years, okay, times, so we're going to figure out something in seconds, right? Because we're going to eventually get this multiplied by meters per second so we can get some sort of meters in there. Does that make sense? So I'm gonna eventually multiply this by 3.0 times 10 to the 8th meters every second. Yeah. I got it, thanks. I appreciate it. I figured it got a little bit bigger than somebody would tell me when it's all good. I got it covered. Alright. So I want to be able to cancel out my seconds. Does that make sense to get something in meters? So I want this thing in meters, I want it to be converted into seconds, I guess. So how do I get years into seconds? Multiply by stuff, yeah? Okay. Yeah, so I'm going to move this out of the way. Okay. So a year has how many days? 365.25. Right? So you can be really careful. Okay? You don't have to. It's okay. Days in 1 year.
Yeah,
quarter, right? 83 whole thing, right? And then, how many hours are in a day? 24. And then, how many seconds are in an hour? Be careful before you speak. You have a hard time with zeros back there. 60 times 60 is?
There we go.
Is that okay so far? So that's going to tell us how many seconds it has taken for that light to get there. Okay? So do that. And it's going to be a big number, I think, yes? So figure out that number if you haven't done so already. Stop being so weird. Oh, okay. Well, sit down. Sit still. Just for a moment. There you go. How many seconds is that? Like a lot, yeah? 6 point what? Times 10 to the 13 seconds. Okay, so that means that the light that's hitting your eye when you go out to look at this thing is 6.9 times 10 to the 13 seconds old. Like, I don't even know what that really means. It's a lot of seconds, though, right? I know that light travels at 3 times 28 meters every second. So I need to do 1 over to do this thing, right? This number of seconds times this thing. Does anyone have seconds on top, seconds on the bottom? That's only the number of meters. Okay? Do it if you haven't done it yet. It's a lot of meters away. How many meters? 2 point what? I don't know if y'all are truthfully. Do you guys believe them? Did you get the same answer? Have you done this? Get a calculator out. Do you have a calculator? Do you have a calculator? Oh, come on! Slackers? I just let somebody else try it. No. Get it out, dude. Because one of you made a mistake. I don't know. It was like, is it a number? Can you corroborate that? Do you agree with those guys? Times 10 to the what? 22nd? Do you agree with that? Is that okay? Now, here's the thing. Like, I don't understand either, right? Here's the problem with astrophysics. Not really a problem. It's more of just like a brain explosion kind of thing. There's just a whole lot of meters. I don't really have a concept of that. This is, like, that's a humongous. This is big, but at least this is a little bit smaller of a number, and so that's why we use this whole light years thing, because you can have a little bit more of a concept of a number that's only 10 to the 6th, as opposed to something ridiculous like 10 to the 22nd, right? 10 to the 22nd of this, like, I don't even know what that means. Except it's really, really, really far away. That's what I know. Yeah.
Is it like, is that from the core?
I mean, a little, yeah, plus or minus a little bit, yeah. Probably about center to center is what that number is coming from. Yeah. Black hole, black hole. All right. Yo. Yeah. Somebody just said, one actually comes back. Okay. All right. Are we okay so far? Okay. So we have this concept now. Okay, well, I'm not done yet. I've got some more time. Okay. So, Zach was asking a minute ago, he said, I heard that if I go out far enough, I can watch the original I Love Lucy's. Yeah? Yeah, the original, you guys know I Love Lucy, right? Like, or whatever. That, like, really old, like, really cheesy, moderately funny TV. Okay, so, when that is broadcast, it is broadcast via light waves, okay? And it's not broadcast directly from the station to your house, right? It just goes out in all directions. One of those directions is straight up. and that would just travel through the atmosphere, and then it just goes through, and just keeps going, right? Okay. So, that I Love Lucy episode that we watched however long ago, right, is out there somewhere, and, you know, there are people that talk about, like, aliens at some point just tweeting, like, wow, that really just really good. I love it. I mean, it's cute. I mean, you get that we have some sort of sense of humor. Right? So that's traveling out there too, but it's not traveling it's traveling the same way, but it doesn't quite seem the same because it's not light. It's not, well, it is light, but it's not visible light. Are you with me there? So when we talk about that, we have to get into this new conversation about what a light wave really is. So a light wave, I will tell you, is a transverse wave. But it's a... Excuse me. I just had this massive cough for like 3 weeks. It needs to go away. It's a transverse wave. It's a weird transverse wave. Usually when you think of transverse wave, like you've got, you know, your spring on the floor and I don't know. But a light wave doesn't quite do that. A light wave is actually a combination of two waves. So it's transverse waves, or transverse wave that's made up of two things. Okay? And it's also weird because it can go through nothing, so it needs to be able to propagate itself. And it does that because it's what we call an electromagnetic wave. So whenever you hear the word electromagnetic, you can just substitute it in for light. Okay? Just makes you sound a little bit more smarter, right? Like, wow, the electromagnetic waves are really strong. Right? That's really right here. Yeah? There's a lot of electromagnetic radiation being incident on you. That just means like it's really bright, it's really sunny, that kind of thing, right? You just sound a little bit cooler, I'm just saying, okay? The structure of an electromagnetic wave looks something like this. This is my model of that. So the way it's set up is that you've got this one set of waves, the purple side, you will see that? And that set of waves is like, it's this electric thing, this like electric wave that's going on, right? And that's where half of the name comes from, electro, right? But then there's also this other piece, the green piece, that is the, this part's the electric, and this part is going to be the magnetic part of the wave, right? And they coexist at exactly the same moment, and they are, like they have crest at the same time, and they have troughs at the same time. You see that they're what they call in phase, so they go together. So they're big amplitudes and a little one, okay? And they travel like this, okay, in the direction of wherever they're going. So that I love Lucy episodes going like that all the way up, and the light from the sun. You know, when little kids draw the sun, right? Like they draw like this and they draw the you're like, yeah, that's not really true. Well, actually, they're smarter than we're giving credit for, really, because there are really electromagnetic waves going out in all of these directions. Okay? So that is really quite true. There's electromagnetic waves going out in all directions in the visible part of light, but also in other parts of light. And this is answering somebody who said it. Was it you, Scott, that said that there are different kinds of light, right? So there are all these different kinds of light. And this fits in with somebody who said, I don't remember, like, it all kind of mixes together in my head here. This whole lambda, what's that? And this C thing and this frequency thing, it all fits together. When you learned about waves, you learned that the speed of a wave was equal to, what do you remember? Do you remember? It's equal to something. Two things multiplied together. F and lambda, right? So let's talk about what those are. So V is velocity or speed. When we're talking about a light wave, you can change V to C because we know exactly what that speed is. It's 3 times 10 to the 8th meters per second. F represents the what? Yeah. What does frequency mean? What does it mean, like, not in a physics context? What does it mean if something's very frequent?
The distance between.
No, you're talking too technical. What does it mean? If something happens very frequently, what does that mean? What does it mean? happens a lot, right? The frequency is very high. The frequency of your mom asking you to clean your room is very high, right? The frequency of your mom asking you to clean your room is much higher than the frequency of you actually cleaning your room, right? So you can compare the frequency. I'm assuming, I'm making assumptions. Maybe it's not true about you. I know it was about me. Probably still is, even though my mom doesn't get on me about it as much as she probably should. Okay? So the frequency is just how often something happens. So it's how often these little oscillations happen. Does that make sense? Okay? So frequency is just how often. So maybe you remember what the units of frequency are? Hertz. What? That's weird. Yeah, frequency is like, so it's the number of times that something happens divided by, or the number of, I'll just say number of times, per measure of time. Like, so it's usually like number like 1 over, time is usually measured in seconds, and there was this guy named Hertz that, studied this or something, and so we got it named after him, or we got it named after him, so Hertz, H-Z. But 1 Hertz is just 1 over seconds. That's all it is. Okay? It's not big and scary and a lot of other things. It's just the name of it. So if you have something like this tuning fork, hey, that had a frequency stamped right on it. It's a 426.7 hertz. What does that mean? So that means that when I strike this, right, it's going to go back and forth, back and forth, back and forth, 426.7 times every second. Okay? That's what the frequency means. And every wave has a frequency. How often does it happen? What is this crazy lambda thing? What's it represent? Not amplitude, good guess. Amplitude is involved, but is not lambda. Where's length? So the wavelength is the length of the... Oh, look at us using our compound words, right? Yeah. Right, so it's just the length from crest to... Did I say the word crest? Does that freak people out? Are we okay? Okay, so from crest to crest or from trough to trough, okay, is the wavelength, okay? So it's literally, let's just write that down, the length of the wave. Lengths are measured in meters. And if we look at the units of this thing then carefully here, I'm going to put it down here, F is measured in hertz, and lambda is measured in meters, but we know that hertz is just, it's not seconds, it's 1 over seconds times meters. And so you've got meters on the top and you've got seconds on the bottom, so if we put those two together, they give you meters per second. And that's just a velocity. Does that make sense? So that's where the velocity thing comes from. So there are these electromagnetic waves, or that makes it sound really fancy, right? Electromagnetic waves, okay? That all move at the same speed, but depending on their wavelength, their frequency also changes. So their frequency and wavelength are directly related. Okay? The bigger one is, the smaller the other is, to make C happen. Okay? And these electromagnetic waves, some of them, just a little tiny sliver of them are the things that we can see. The things that we call visible light. And then there are a whole bunch of electromagnetic waves, or electromagnetic radiation, if you want to sound even fancier, right? Like let's, I mean, if we're going to sound fancy, let's make ourselves sound really good, right? That live in what they call the electromagnetic spectrum, but not things that you and I can actually see with our eyes. So you may have seen a picture like this before, or something kind of like it. And I'm going to tell you, I want you to write some of this down. You don't have to write every single bit of it down, because that's a lot to write down. So on your paper, get yourself a little swath of paper, or swath, a couple of lines or something like that. And I want you to write down just some pieces, and then we're going to talk through each piece. So the first thing I want you to write down is this one right here. It says gamma. Oh, what's that? Gamma. Look up here at our alphabet. Alpha, beta, gamma is the third letter, okay? And if you're going to write it, it looks kind of, I don't know, like that. Kind of like an upside down, I don't even know. Like an upside down L. Cursive L. Does that make sense? Yeah. So right now I just want you to write these down. It's kind of in order on your paper. Okay? Gamma rays. The next one is X-rays. You've probably heard of those. You probably had some incident on your body at one time or another. The next one is UV. Ultraviolet. You've heard of these, right? These are the ones that we're always scared of when we're outside playing during the summer. Then the next one is visible. And it's interesting because if you notice, all of light that we think of when we think of light is just this little tiny sliver in this whole big thing. After visible then comes, it's labeled IR. What does IR stand for? Infrared. Thank goodness we know that infrared exists because that's how we do a lot of communication, short distance communication. Then we've got another one of our favorite appliances, the microwave. The microwave that you have in your house utilizes microwaves. Okay? And then after that, it's just one more, it's just a lot of it, and it's radio waves. Okay? So that 1, 2, 3, 4, 5, 6, 7, those 7 things, write those down. We're going to go through them one at a time. You don't have to have all the details written down. I just want you to have those 7 labels written down. Have you heard of most of those words before? Yeah? So here's the cool thing. These are all electromagnetic waves. These are all light. So again, if you want to sound smart, you want to sound cool, then you can talk about any of these, right? Ultraviolet waves are just light. Infrared is just light. Radio waves, what? The waves that carry our data to our radio, that's what we're really talking about there, are also light waves. Okay? If you look at these numbers, you'll notice that the numbers start out on the bottom here really, really small and get really, really big. Like really, really small, we're talking 10 to the negative 16th. Look at the negative 16th, that's like really little, right? Okay, meters. And they go out to 10 to the 8th meters. What is this a measure of? If it's measuring meters. Wavelength, right? From crest to crest. So when we're talking about gamma rays, we're talking about things that have between crest and crest on that way 10 to the negative 12 meters. That's like so little, like so little. When we start talking about radio waves, like at the beginning we're talking about like on the order of this big, from crest to crest. Okay? So a radio wave is like this big. Or like hundreds of these or thousands of these, depending on how big your radio waves are. You may want to write down on your sheet you got over here increasing wavelength when you go in that direction. And if we know that C is equal to lambda times F, if the wavelength goes up, what has to happen to the frequency? Has to go down. So if you look at this one carefully, it says that it's increasing frequency in the other direction. And the secret that you may want to know here, and this will explain some of the fear behind this stuff over here, is that as frequency increases, the energy of the wave also increases. So why are people, just kind of in general, so afraid of ultraviolet light? What does it do? It'll burn you, right? Sunburn, yes? Yeah. How does it do that? Do you know? John? And then it burns you. Yeah. So the deal is, the reason, like, so if I just stand here under this light, is this UV light here? What kind of light is this? It's coming from that light. Visible light. If I just stand here like this, am I going to get sunburn? No. Why not? The energy is not as big, right? Okay? The energy is not as big, and you can also think about it in terms of the wavelength. The wavelength is much, much smaller for ultraviolet. Okay? That means that it can actually penetrate into your skin cells. Okay? And that's how the burning happens. That's how the destruction happens. And it's less the sunburn. What's the really big scary thing about ultraviolet light? What can it cause? It can cause cancer. What is cancer? It's a what? It's a mutated skin cell. Right, so if you're talking about skin cancer, right? So the light comes in, and it mutates the cell, right? It causes it to not be able to reproduce in the same way that it should. Is that okay? Does that sound okay from your biology experience? Okay? And at that point then, you've got a problem happening because of this high energy light. Have you all had x-rays before? No? Like at the dentist?
Yes.
Oh yeah! When they get the little annoying thing in your mouth, they say, clean your tongue, don't hold on! Right? And they put a little thing on. And then, right, you know what I'm talking about? Right? So they're using, they are like, this is what they're doing. They are sending high energy electromagnetic radiation, right, light waves into your mouth. Why? Why do they use x-rays? You can see through what? Yeah, so if you've ever, like, broken a bone, they use x-rays too, right? So let's think about what's happening. The light wave is going into your skin, right? And does it bounce off your skin? No. Visible light bounces off your skin. That's how I see you. I see you because light hits you, it bounces off when it comes to me. Right? That's how we see each other. Okay? But x-rays are going to go through your skin because their wavelength is much, much smaller, so it can actually penetrate in your skin. It's going to go through your skin and through your muscle. What does it bounce off of? What do we see? The bone. That's why we use x-rays. X-rays go in, they bounce off of things that are much more dense. Bone is much more dense than skin and muscle, right? So it goes in, it bounces off of the thing it can't get through, right? And then that's why you use x-rays to see what's going on when you're looking at bones, okay? X-rays can be dangerous if you expose yourself to them too much. I don't know if you remember hearing about, like, the TSA, like the flight safety people, right? They were trying to, like, bombard people with even more x-rays when we go through the safety stuff. And we're like, oh my God, it's really x-rays, blah, blah, blah. Because they can cause, what? Cancer. In the same way that UV causes cancer, but it's going to cause cancer in a different place. Now, if you have x-rays that are coming in right in your mouth, and not for very long and not very high intensity, then it's going to be okay. So it's not like he's like, no, never give me x-ray again, right? Because there's that balance where you have to have like the safety versus whatever. But if you just bombard yourself with x-rays all the time, this is when problems happen. Okay? Gamma rays are even, people would say, scarier. But you're going to say that gamma rays just have a whole lot more what? Energy, right? A very, very high frequency and low wavelength, tiny wavelength, which means that instead of bouncing in and bouncing off of your bone, what are they going to do to your bone? They're going to go into your bone, right? Right? So that means that a gamma ray, again, just a piece of electromagnetic radiation, that's all it is. It looks just like this. It's the same deal as the light that's coming from our sun and from everything, okay? It's just a very, very, very small wavelength. It can get in much, much further. Does that make sense? It's all the same deal. It's just that these are more energetic, okay? If you've ever heard of like radioactive elements, okay, like nuclear power, and they get really scary with like radioactivity and stuff. It's from the high energy particles like this. Okay? That can cause problems, if you are bombarded by them too much.
He's been treated as fired by the first.
What?
He's been treated as fired by the radiation first. Wow.
Right, because all of that story is true.
That's character.
Right, okay. Let's go this way. What's that? Infrared. Infrared. What do you use infrared? What's that? What did he say? Okay, tell me more. I don't know Call of Duty, so tell me when Call of Duty you use infrared. Like always, like infrared. What? Tell me more. If you're gonna bring it up, we gotta talk about it. Okay, so let's talk about this, yeah? So, your body gives off heat, yes? What is heat? Which is just electromagnetic radiation, right? You glow. You glow. Now, here's the thing. Do you glow with the visible light of the spectrum? No, and I can see you because there's light that's bouncing off you, but if I turn the lights on and I close all of the visible lights, there's no more visible light in this room, and I can be able to see you? No, because there's no light bouncing off of you. But when you're doing these crazy things, you want to see people. Here's the thing, is that you do glow. Why do you glow? Do you know why you glow? What is energy? What is that? That was a really frightening noise that just happened back there. Do you want to explain what that was? Okay, so if you want to go there, it's interesting when more than half of you, because more than half of you, some of you will probably choose to have kids, and some of you will interact with weird people when you are pregnant. I'm just warning you because people are weird. One of the things that people will say is they're like, oh wow, you're getting fat? Is, oh, you're glowing. And then you have like a really nice feeling like, you look good, right? But it's like, really like, no, you're fat, right? Like, but, so as a physics teacher, right, when people say, oh, you're glowing, and people do this a lot, like people are weird. My response in my head, I don't actually say it out loud because I don't want to sound like a complete jerk. Like I just say this to people in my head. I say, yeah, I know, and you are too, right? Like, we're not glowing in this part of the spectrum, but we're glowing here. Why? What causes us to glow? This is chemistry stuff we touched on. Right? So your body, the molecules in your body are moving, yes? Okay? And actually, this is weird. When they move, they give off these things. The vibrations that they give off are in this part of the spectrum because of the frequency with which they vibrate. Whoa, look at me! Yeah, right? If you are glowing, you're just glowing in a different part of the spectrum. So you put these goggles on, right? These goggles that perceive stuff in this part of the spectrum and convert it into visible light. And that's how you see heat. What's that? And that's when you glow. Yeah, so then you're like, I know, thanks. This is like, everything glows. Everything glows. Everything glows. Unless it's just what? Unless it's just zero. So everything glows, just going to glow as, but not in the same part of the spectrum. Well, that's why Call of Duty is not true. Alright, ladies and gentlemen, you just have to tell you something. Listen, please. So first of all, thank you so much for your attention today. I hope that this was a helpful day of learning things. I do want to make sure that you have read the first two sections of the book from chapter 13 before you come in on, Thursday. And one last thing, I have a student who's out finishing a final for me. Like, this is a big, scary final. He's sitting right up there, so please, as you're reading, be very quiet until you